Swayam Prabha. Digital India. Educated India.
Hello, Namaste. I'm back with the next set of lectures on geographic systems. Specifically, as I said in my previous lecture, I would be speaking on the coordinate systems. So, understanding this coordinate system is extremely important and extremely essential when you have to work on a map. Okay. So when we look at this entire lecture is being divided into some concepts like coordinate reference system, which is also called as CRS. Then we look at geographical coordinate system, or called as GCS in simpler terms. Then geographic coordinates. What do you mean by geographic coordinates? Geodetic datum. Okay. Then representation of the earth. So we'll cover all of these topics in this particular lecture. The first thing, when we look at the coordinate reference system, whenever I refer CRS, it is nothing but a coordinate reference system. So when I say coordinate system, it is an XY grid upon which, so it is always an X and a Y. So it's XY grid, okay, upon which a GIS data is overlaid, and how we define a point that is located on the earth's surface or in the space. Okay. So now horizontal and vertical units, these are the units that are used to define the grid along the XY, and if in case it's necessary, Z axis or Z axis. So when you look at this, a modeled version of the shape of the earth which actually defines the origin used to place the coordinate system in space. So it is the origin used to place a coordinate system in space. Okay, that is nothing but a datum. Okay. So when we look at datum in more pictorial form, so you will understand what is a datum. Then is the projection information. Projection information, when we look at it, the mathematical equation that is used to flatten a 3D object into a 2D object. Okay, a 3D round earth shape into a 2D flat map, then it is called a projections information. I spoke about this in my first lecture of this particular module. So whenever we look at coordinate referencing system, we have to look at coordinate system, then look at the vertical units, horizontal and vertical units, that X and Y, and in many cases as Z axis. Okay. Then look at datums, and finally look at the projection information, without which your CRS would not stand. Okay. So keep this in mind. So whenever you are looking at CRS, look at all of these 4 quantities, then only you will be able to understand the CRS. There are 2 important systems in the earth reference system, referencing system, so coordinate referencing system. So be very careful. So these are the 4 different quantities that we have to see, that I explained in my previous slide. But in order to reference, you have 2 types of system. One is called as a geographical coordinate system, is a system for identifying locations on the curved surface of the earth. But there is something called as a projected coordinate system, is a reference system to identify location measuring on a flat map. So when you see GCS, it is more of identifying location on the curved earth surface, and when you are looking at a PCS, that is a project coordinate system or a projected coordinate system, it is on a flat map, it is on a 2D map. So keep this in mind, these are reference systems. Okay. So when we look at geographical coordinate system, it's normally is in decimal degrees and are helpful when you need to locate a place on the earth. For example, a very good example that probably many of you have looked at is the Google Maps. Okay. Sometimes when you are actually hovering, I would suggest something like this. If you are looking at this particular lecture, open up your Google Maps, okay, and open up a particular place where you may have to travel maybe tomorrow, day after tomorrow, etc. Look at the distance from that to that particular place. Fine. Now you are comfortable at looking at that distance. Now just take out that red pointer and put it somewhere else which the map doesn't have a name. So what does it show? It actually tells you the x and y of that particular place, that is in terms of maybe in degree decimals or in degree minutes and seconds. Yes, that is what I am speaking about, the GCS system. So latitude and longitude locations are not located using uniform measurement units. Please keep this in mind. That is what is one of the major disadvantage of the system. So GCS are not ideal for measuring distances, and other projected CRS have been developed to address this particular issue. If you have to measure distance, then latitude, longitude, the way the GCS works is not the way you use it. But if you have to use the measurement system, then use a projected coordinate system. The GCS locates latitude, longitude location using angles. Thus, the spacing of each line of a latitude moving north and south is not quite uniform, which you can look at it here. Okay. So a GCS, when you look at a GCS coordinate system, the lines that are moving to the north or the south is not very uniform, and you can never measure anything as a distance measure in a GCS system, whereas in your projected coordinate system it's much easier to understand. When you look at geographical coordinates on the Earth's surface, mainly you would have seen it in the form of a latitude and a longitude. When I say latitude, these are measured in degree north or south of the equator, also known as parallels of the equator. Okay. Longitude also measured in degrees east or west of the Greenwich prime meridian, also known as parallels of meridian. So when we look at this particular example here that I have mentioned, if this is your Earth's surface that you have considered, okay. Now we know equator is central part of the line that is passing to the center of the Earth's surface, which is 0, okay, 0 degree. Now if you start drawing lines at this, something like this, these are latitudes and in as northing. When you are writing this is towards the south, these are latitudes. So when you draw latitudes, all are in north and south latitudes, and if the same thing, if you start drawing like this, these are longitudes. Okay, this is, if this is 0, this is the line that is easting and westing. From here you have easting, and from here you have westing, something like this. This is a prime meridian which is 0, you have 30 degrees, 60 degree east, whereas you have 30 degree west and 60 degree west. Now my prime question to many of the students would be something like this: I have an Earth surface something like this. Now this is your 0 equator and this is your 0 prime meridian. Okay. Now if someone wants to locate a latitude, on which axis you would measure to actually locate a latitude, and which axis you would measure to locate a longitude? So the answer here is, if you are locating a longitude, for example, if you write longitude here, so now it is actually intersecting on the x axis. So longitude measurements are on the x axis, but it is represented as y. Okay, because you have x axis representing, these are longitude measurements. Now if you want to do a latitude measurements, so what you would do, let us say this is Earth's surface. Now this is your equator, right? So you want to do a latitude measurements, which means if this is your prime meridian, if you start having the north thing here, 30 north, 60 north, 90 north. So now you are intersecting on the y axis, right? So your measurement is on x values. Okay. So x comma y. So latitude comma longitude. This is how you arrive at it. So please remember, longitude will have its marking on the x axis, latitudes will have marking on the x axis, on the y axis. So this is where most of the students make a mistake. So please understand how the latitudes are marked and longitudes are marked. So clubbing this will give you the entire Earth's grid. Okay. So once we have understood this, we'll move on to the next understanding. Latitudes and longitude are defined using an ellipsoid or a spheroid, an ellipse rotated about an axis. Okay. Elevation is defined using a geoid. Okay. A surface of constant gravitational pull. We have already looked at it. And earth datums define the standard values of the ellipsoid and the geoid. Okay. So when we are looking at the geographical coordinate system, when we look at the entire earth grid, it is actually formed by combining the entire latitude and longitude. So you cannot say, if you are located at this particular point in India, so you cannot say that this is at only latitude of this. You have to represent latitude and longitude, then only you will be able to very clearly say this is the point on the earth's surface where I am located on. So you have to give both latitude and longitude in reference to equator and one with reference to Greenwich prime meridian. So without which your entire earth grid is not complete. Okay. So a coordinate system is basically a standardized method. So how do you define a coordinate system? Is just as a standardized method for assigning codes to location, so that location can be easily accessed by just codes. Okay. My latitude, longitude are just as codes. Using those codes, anyone can find. So if let's say there are 4 people who are looking at 4 different locations, if we have the same way of looking at this, or same coordinates that we are actually looking at, and everyone is looking at latitude, longitude of a particular place, so it's easier for us to compile the data. If it is completely different, then it may not be easy for us to compile the data. So it is a codes to understand a particular place, region, a phenomena, etc. Okay. Then standardized coordinate systems use absolute locations, exact locations. A map captured in the units of a paper sheet on which it is printed is based on relative locations or map millimeters. So that we have to remember all the time. In a coordinate system, the x direction values is the eastings and the y direction value is the northings. So that I have already shown, x direction value is the eastings, y direction value is the northings. So please keep this in mind. I have already explained how latitude and longitude is measured, where latitude intersects and where longitude intersects, and how the values are measured in a latitude and longitude system. In a coordinate system, the x direction values is easting and y spread. Most systems make the values as positive. Fine. Then next comes the geocentric coordinates. Geocentric coordinates was used in various ways. It is extremely important in terms of when you are trying to make the measurements. So geocentric coordinates are based on a rectangular coordinate system with the origin at the center of the earth's surface. So if we consider this is the center of the earth's surface, the z-axis is a coaxial with the axis of the center of the earth. So if you are representing the z-axis, if this is the center of the earth here, okay, if you consider this as center of the earth, this is coaxial from the center of the earth. Then the x-axis is through the 0 meridian. When you are looking at the x-axis, it has 0 meridian and in the Greenwich, and y is orthogonal to the earth axis. So this is orthogonal to the plus x axis. Now when you are looking at geocentric, you have plus and minus also located, and we will look at some examples as we go to the next slides. So but when you are looking at geocentric systems, it is the first thing that you have to understand is geodetic datums. Geoid models attempts to represent the surface of the earth. If you are looking at this as a surface of the earth, it is actually representing the entire surface of the earth where both land and ocean through surface resulted from the gravity alone. Okay, so now this is measuring in all the surface of the earth, it is okay, but it is based on the earth's gravity. Okay, geodetic datums define the reference system, so be very specific here, that describe the size and shape of the earth and the origin and orientation of the coordinate system used to map the earth. So now when you are looking at this, okay, the thing that you have to look at, geodetic datums are defining a reference system. Okay, then it describes the size and shape of the earth. What is the size of the earth? The shape of the earth, and origin and orientation of the coordinate systems. So all of these together will form a datum. Okay, so mean sea level is a surface of the constant gravitational pull, which I have already spoken about in my previous class. Okay, so when we are looking at geoid, let me go back to my previous slide. So when we are actually looking at a geoid, we are actually looking at a constant gravitational pull on the earth's surface, and this is called as a reference grid or a reference point. So when you are looking at referencing any geodetic coordinates to a wrong datum, it can actually replicate the positional errors to hundreds of meters. So if you are using a wrong datum and you are trying to reference a particular system, then if you are measuring it in India, it can even fall in somewhere in Africa or America in terms of where you are placing your map. Then different nations and agencies use different datums, okay, as the basis for coordinate systems used for identifying positions in the geographic information system. So please remember this. So whenever you are looking at datum, it can be in any different datums, but you can always convert it to the datum that you are actually looking at. Okay, to give you much detailed understanding, if this particular line, that is a brown line as I am drawing, is the earth surface, okay, and the dotted line here is your sea surface that we are trying to see, okay, and if I draw a line that is actually looking at the mean sea surface with a constant gravitational pull, then it becomes your geoid. Okay, so as I said, earth's surface is nothing but an ellipsoid. Okay, so looking at a geoid is something like this. So now when you have your mean sea level which is equivalent to a geoid, okay, if you have a mean sea level that is equivalent to your geoid, if this is your mean sea level, so your elevation z is 0. As you go on above, your elevation will be equivalent to the point that is measured from the mean sea level to the height of this particular place. That gives the elevation of that particular region, which means elevation is nothing but mean sea level plus Zp in meters. Okay, so next time when you actually go to any of your railway stations in your city, your region, please look at what is the elevation your city is in or that particular railway station is in. So you will get a fair idea of, if you are moving in different cities, different regions, then you will be able to get different elevations, where the city, which elevation is in the higher point and which is at the lower point. So you will understand the way of representation of the earth surface, or how the earth surface is there in the entire Indian subcontinent. Okay, so now let us go to the examples of geographic coordinate system. The very well known geographic coordinate system is the word geodetic system. This particular geographic coordinate system was established in 1984, that is why it is called as WGS 84. This geoid reference the geoid height from the entire earth. So it is mostly used geographic GCS system. it fits well for most of the countries across the world. So most of the work that is done today is in WGS 84. Okay, if you find I mean most of what whoever does is in common with this particular system. Then you have the global positioning system, which uses the WGS 84. So now the collection system where you are collecting your data is also in your WGS 84. It is fair enough to use your system also in WGS 84. So it is representing an earth model in terms of a WGS 84. Normally it is in the form of a meters. Both the measurements are in the form of a meters. Okay, so understanding this, will also go into some examples of other geographic coordinate system. The very basic geographic coordinate system for Indian subcontinent, you can see maybe if someone has used some of the older satellite data products, it used to come in the Everest or Indian datum system. So this used to be the reference system that we used to use, but today we can get in WGS 84 directly from the National Remote Sensing Center. So Survey of India uses the Everest datum for more than 150 years to map the entire country along with Nepal and Pakistan and Bangladesh. Okay, so named after India's first surveyor, General Sir George Everest. So it is not with as many in, if you see in many of the theories, they say it as based on the Mount Everest. No, it is based on the surveyor George Everest. He was the first one who surveyed and made the physical geographical representation. The Indian spheroid has been marginally modified on a number of occasions. For example, Indian 1880. So that is again is called Everest 80. Then you have Everest 1930 or Indian 1956. So these are different ways where this particular system has changed. Now, for example, whatever we saw in WGS 84, there is a small change when we look at Indian system. Now, what is that particular change? If you look at, as I said, if you take this as the Earth's surface that you have, okay, if you are taking this as the Earth's surface, okay, now this is your geoid, okay, this is what, something like this, okay, this is the one that is for Everest. If you look at WGS 84, you have something like this. Okay, so each of this is representing, this is a Clark 1866. I will take some other color. So Clark 1866, this is representing the Everest 1830. Then you have this representing the Everest ellipsoid. So ellipsoid is also important, and this representing the Earth center. So now each datum has a different Earth centers that is clearly mentioned here. So and based on that, you look at the topographic surface, and based on the topographic surface you fix your the entire datum. Okay, that is what Indian datum is based on. That's how it is different. But nowadays mostly it is not used, whereas WGS 84 is much used in various applications. Okay, so then another example of a geographic coordinate system is a NAT27. This used to be used heavily when this particular datum was used, actually introduced in 1927. Okay, so this particular system was had been took over by Clark 1866 spheroid with the datum and fixed the lat long at Kansas. So now this particular datum fits North America very well. So there are certain systems even today where NAT27 is used in a very prolific manner. So NAT27 system is extremely useful in North America, but whenever it comes to other continents, it is a bit distorted. So using the same NAT27 system in terms of using it in the on Indian subcontinent may not be much useful. But whereas if you use Everest in the Indian subcontinent, it is of much useful. But because of the complexity involved in terms of having it on the system and converting it to other types, this particular average system is not used. But WGS84 is one system which is extensively used across the globe. Anyone who is working on the aspects of a map today uses a WGS84 system. Most of your satellite data, most of your data from different sensors, etc., are georeferenced using the WGS84 as a geographic coordinate system. So I would suggest, and we would also in the course of giving certain examples, or when you are looking at the software, we would primarily stick on to WGS84 as a geographic coordinate system. Okay, so with this, now let me summarize today's class. So when we look at the coordinate reference system, we have two types of referencing. One is geographic coordinate, another one is polar coordinate. So when we are looking at this, we have latitude, longitude as the referencing system, but when we it may not be very useful in terms of measuring the distances. When you look at geodetic datums, these are measuring elevations on the Earth's surface. So please be careful. So you have, I hope everyone has understood what you mean by a datum, what you mean by a coordinate system. So then we looked at the representations of the Earth. So please remember, this representation of Earth is to represent how a particular land mass is then subdued from the third dimensional Earth to a two-dimensional Earth, where it can be easily interpreted. Otherwise, it is much difficult for anyone to visualize what is there on the Earth's surface. Then representations of the Earth's surface that we have seen, the examples of different GCS. So I am repeating again. So WGS84 is much referred system. We have various other systems. If you just open any of your toolboxes, any of your software, for example, and just go to the georeferencing tool, and if you open up the referencing system, you can find a huge list of referencing systems. So each country has its own way, each particular organization has its own way, each particular user has his or her own way of representation. So there are huge number of referencing systems. So but with this huge number, when you look at the Indian subcontinent, it is the Everest referencing system that is used the most, okay, which has evolved over a period of time from 1800s 1880s to till 1956. But now it is not much of use, or it is not much used in for a referencing system, whereas WGS84 is much used in all terms, because easiness in terms of measuring any distance of any object on the Earth's surface. So that we have seen. Then we looked at NAT27, then which is actually for the only for America, basically North American part. It is extremely useful, but in other continents it may not be much useful in terms of applications. So now we have understood what is a coordinate system, what is a coordinate system, what do you mean by coordinates, what do you mean by a datum and a geoid, right? So in the next class we'll understand what is a map, how do you represent a map, what are the different standards of representing a map. Then if you have to build a map and present it, how do you actually present it? And if in case you want to search a neighboring map, how do you search a map, how particular map numbering is done as far as Indian subcontinent is concerned. So all of this we'll look at, but only thing that you should remember, whenever I am going to speak about GCS, please remember all the things that we have learned from the datum to your coordinate system. Once we have understood what the map quality is, then we will look at what you mean by a projection. So that is the last part of this particular module, where we would be looking at how do you project the Earth's surface onto a map and what are the different qualities that you have to see. Thank you very much. So we'll meet in the next class.